So we're starting chapter 14, which is comparing groups in an analysis of variance. This material is a continuation both of what we did in chapter 10, where we had bivariate situations with a categorical predictor, but only of 2 levels, or 2 independent groups and quantitative response, but also a continuation of what we saw back when we did regression, both simple regression and multiple regression. So we're going to see both of those ideas in chapter 10 and chapters 12 and 14 come together here. So we're going to motivate this now with an example. Say you're interested in buying a new car and your initial criterion is fuel efficiency. So that is, we're going to look at the miles per gallon for these cars. You want to know whether American and Japanese automobiles get the same gas mileage, so that's miles per gallon. So you get a random sample of 70 American-made autos, and that sample has an average mileage of 20.49 miles per gallon and a standard deviation of 5.47. You also have a random sample of 79 Japanese automobiles with an average mileage of 30.85 miles per gallon and a standard deviation of 6.36. So we have y bar 1 equals 20.49 and S1 equals 5.47. We have y bar 2 equals 30.85 and S2 equals 6.36. We also have N1 equals 70 and N2 equals 79, right? So we can see that these are independent samples because an automobile cannot be both American-made and Japanese-made, right? And there's no evidence of matching across these 2 samples. So this is independent samples, right? So this is independent. So this is what we did at the beginning of chapter 10. So to test this, whether there is an association between where a car is made and the mileage for that car, or for the type of car, is going to be mu1 minus mu2 equals 0. In this case, there is no association. And then the alternative is that there is an association, that is, knowing where a car is made tells us something about the average mileage. So that would be mu1 minus mu2 is not equal 0. There is a difference in the mean mileage, or knowing that a car is made in America or knowing that a car is made in Japan tells us something about the average mileage. Or that the average mileage changes depending on where the car is made. And of course, we then define mu1 and mu2 in context. So this is just what we did in chapter 10. All right, we would use the pooled standard deviation because S max over S min, in this case S max is 6.36, S min is 5.47, and 6.36 divided 5.47, that's much less than 2. And N1 and N2, 79 and 70, they're about the same. Of course, they're not exactly equal, but they're pretty close. So we can assume equal standard deviations. So we can assume sigma 1 equals sigma 2. So it's appropriate to use that pooled standard error. And if we do that, our degrees of freedom is N1 plus N2 minus 2. And in this case, that would be 79 plus 70 minus 2, or 147. So all of the work is reproduced below. So our pooled standard deviation is the square root of N1 minus 1 S1 squared, plus N2 minus 1 S2 squared, etc. And so our pooled standard deviation is 5.959. So we can see it comes down between our 2 sample standard deviations. And we use this to get our pooled standard error. So this is the square root of MSE. So we get our standard error, and we find our test statistic, T obs, by taking the difference in our sample means, dividing by the standard error, and we get a test statistic of negative 10. So this means if there is no difference, we found a sample difference 10.592 standard errors below the true mean difference of 0. But that if there is no difference is key, because if there is no difference, then the true mean difference is 0. All right? We were able to use the t-distribution. We were able to do this whole situation because of some of the key assumptions we made. So this is reviewed from chapter 10 as well. The first assumption is that we have random samples. So we have a random sample of American cars, which was stated, and we have a random sample of Japanese cars, which is also stated. So these two sample means we have y bar 1, y bar 2, or is listed in this test statistic, x1 bar, x bar 2. These are representative of the true population means. Right? We also have to have independent samples. That is, the sample of American cars has to be independent of the sample of Japanese cars. There's no overlap between those samples. What's going on in American cars can't influence what's going on in Japanese cars. The mileages can't influence the other samples. And that is true, and we talked about that already, that there's no overlap. An American car can't also be a Japanese car and vice versa, and there is no matching. So both of these have been satisfied. We also have to have a quantitative response and a categorical predictor. And this was satisfied. The response is the mileage, and the predictor is the country of origin. And we have to have a normal response for both populations. That is, mileage is approximately normal for American and Japanese autos. Now, we don't know this. It's not provided. It's not stated in the problem, and we don't have the sample data to look at the sample distributions to see if it's reasonable. So this is a true assumption. And then finally, sigma 1 equals sigma 2, because we checked S max over S min is less than 2. And that's what we did up here. But we also know that cars aren't only ever made in 2 countries. We know that the European Union also manufactures cars, and this data table is split across 2 pages. So we've got our original sample of 70 American cars, our original sample of 79 Japanese cars, but say you also have a random sample of 60 European cars with a mean of 44.68 and a standard deviation of 5.13. Now the question is still, is there an association between where cars are made and their mean mileage or their mileage? So the question still remains, does knowing where a car is made tell us something about the mileage of those cars? But now we have to think about how we're going to answer that question. Now, if this was a quantitative predictor, we would do regression. But we have a categorical predictor, so regression isn't exactly appropriate. We don't want to look for a linear association. We're just asking about association. Because it could be, for example, that, if we were to plot these means, we see right here we've got US, Japan, and Europe. But I could rearrange these so that it would be, US, Europe, and Japan, and my means would go like this, and that's not linear, but we can still see that there is a change in the mean response, and that's what we care about. So one way to find out if there is a difference in fuel economy or if there is an association, we could do 3 separate t-tests, and so that would be US versus Japan, so that's one test, US versus Europe, that's another test, and then compare Japan versus Europe, so that's another test. But this can be problematic because every time we do a test, this is got alpha, this has an alpha, and this has an alpha. And remember, alpha is the type 1 error probability. It's not just some arbitrary number. So every time we do a test, if we reject, there is a chance that we've committed a type 1 error. So we have to worry about our type 1 error rate. And so I could reject here, but I could have committed a type 1 error. I could, with this next test, reject, but I could also commit a type 1 error. And with this last test, Japan versus Europe, I could commit a type 1 error as well. And if I do all 3 tests, I could commit exactly 1 type 1 error. I could commit exactly 2 type 1 errors, or I could make a type 1 error for all 3 tests. So the probability of at least type 1 error among all 3 tests isn't 0.05, it's actually 14.3%. Because I could make an error on any one test, any combination of two tests, or all three. And so I might think that I've only made a type 1 error 5% of the time, and that might be what I claim to my readers, to my boss, to whomever I'm reporting my results to. But in fact, the more and more tests that I do, the higher and higher and higher the chance or the probability that I commit a type 1 error gets. And this is one of those problems that the article that I asked you all to read is trying to address. So there's this reproducibility crisis, there's this replication crisis in the sciences, and one of the things that they're addressing is this issue of p-hacking. And one thing that can result in this p-hacking, one thing that can lead to p-hacking is just doing lots and lots and lots of tests, because if you keep doing this, eventually, right, if you keep just doing one test after another, eventually you'll find something is significant, even if it's not. And that's this increase of the type 1 error rate. And so that's bad science, bad statistics. So if we can keep conducting more and more tests, the probability of at least one error, the probability of finding a significant result when there really isn't a difference, increases. So say there were 10 comparisons. So that is, say that there were 10 t-tests of two groups at a time. And to do that, that would mean there were 5 groups total. So that would be like US, Japan, Germany, England, and Italy. Let's compare Lamborghinis in there, for example. So instead of saying the European Union, we'll break that out into 3 countries within the EU, right? And so if we just have 5 groups instead of 3, so with 3 groups, US, Japan, and Europe, there are 3 t-tests we can do. But if there are 5 groups, that blows up to 10 possible 2-sample t-tests. And as we just said, the type 1 error increases. Well, how much does it increase? The probability of at least one type 1 error among those 10 possible tests is now 40%. So just by increasing the number of groups that we're interested in by 2, we're blowing up from 14 to 40%. Nearly half the time, we're going to find a difference when it doesn't exist. So maybe 2-sample t-tests aren't the way to go, right? So the more and more and more groups we compare. So maybe we'll also include French cars and Swiss cars and, so on and so forth, right? We're just going to keep increasing our type 1 error rate. So this problem is called the galloping alpha problem. And sometimes it might be called the runaway alpha problem. So if we fix the significance level, if we fix alpha, the type 1 error rate, for the individual t-test to our usual values, we end up with a very large type 1 error rate after all is said and done. So what we'd rather do is just do one test that tests all these comparisons all at once, and then with one test, there's only one opportunity to make a type 1 error, and then that we can fix to 0.05. So to do that, we're going to do what is called one-way ANOVA. So that's one test, which is that analysis of variance. So this is where regression is coming in. So we're going to be comparing those means, the mean mileage for American cars, the mean mileage for Japanese cars, the mean mileage for European cars, with one test. And this is going to be very similar to what we did for regression, where we compared the effect of multiple predictors all at once. So here is one plot of our fuel economy data. So this is that, sample mean. So this is about 22, this is about 30, and this is about 44, the sample mean mileages for those 3 groups. This red line, this is the grand mean y bar. And what we did before, when we thought about the two-sample t-test, what we thought about regression was we talked about explained versus unexplained variability. So our between group variability, so this is talking about how different our group means are from the grand mean. This is like saying, how steep is the slope? But I'm going to put slope in quotation marks because we don't have a quantitative predictor. So this is also saying, how big is the change from one group to the grand mean? So if we had a steep slope, then our predictions were very different from the grand mean. We had big explained variability. In this case, we see that our orange arrows here are very different from the grand mean. Well, if I had to predict for the US, my best guess would be this 22 miles per gallon. If I had to predict for Japan, my best guess would be that group mean, the 30 miles per gallon. Similarly, if I had to guess for Europe, I would guess that 44 miles per gallon. Those are my predictions. And they are sometimes very different from the grand mean, and that is what is represented by these orange arrows. All right? So if all of my orange arrows, or if at least one of my orange arrows, are very different from the grand mean, then I've got a pretty big change. That's like having a steep slope. This is my explained variability. Because I can explain the differences between the US and the grand mean, Japan's mean and the grand mean, and Europe's the grand mean. I can explain it by saying, yeah, those are different because they come from different countries. They were made in different places. What I can't explain is why a car all the way down here, or an automobile all the way up here, why they are not all the same. They all come from the same place. They're all manufactured in the United States, but I don't know why this car is only getting about 9 miles per gallon and this car is getting nearly 40. Similarly, I don't know why this Japanese car is only getting about 18 miles per gallon and this one's getting 48. And I don't know why this European car is getting 30 miles per gallon and this one's getting 55. I can't explain the variability within each group. That's like saying, I don't know why some of the plain packs had as few as, 13 candies, and some of the plain packs had as many as 19, right? That's unexplained variability. It's differences within the groups. This is the same as saying how different are my observations, if we're thinking about regression, around the line. We'd like our within group variability, or my unexplained variability, to be small, just like we want our explained variability to be big. So what ANOVA does is just what it did before, and just what our two-sample t-test does, is it compares the fuel economy variance between groups. That's my explained variability, against that within groups. That's my unexplained variability. So let's consider a different scenario. What if my means are the same, so my predicted responses for each group are the same, but my standard deviations are all now doubled. So my standard deviations have increased. So these orange arrows are the same size. My between group variability is the same. My within group variability, though, is bigger. So now, if we compare these two plots, what I had before was relatively clear separation between my groups. I could see pretty clearly that Europe was different from Japan, was different from the US. If I had a car that had 29 miles per gallon, I could pretty much tell, so 29 miles per gallon is right about here, I could pretty much tell that it had to be from Japan. It was going to be very rarely from the US and very rarely from Europe. Down here, if I have a 29 miles per gallon car, it could very easily be from the US, it could be from Japan, and it could possibly be from Europe, right? So there's less distinction between the groups. If we relate this to regression, this plot would be like one that has a steep slope because there's big explained variability, right? There's big differences between my group means and the grand mean, but I've got a lot of residual variability. I've got a lot of unexplained variability going on. There are huge differences within each group. If I consider my original plot, I've got that same big slope, but the differences within each group, that is the variability around the line, is much smaller. So I have stronger evidence in this first plot when I have small within group variability for a difference, for differences between my groups, than I do here. Visually, I can't tell these groups apart that well. Up here, I can tell these groups apart much more easily. Is there overlap still? Yeah. As much? No. So, when comparing means using ANOVA, we're going to follow the same steps of any hypothesis test, but it's only the specifics that change. The hypotheses, the test, the conditions, the mechanics, and the conclusions are going to be very similar to what we saw when we did regression, and it'll be very similar to what we saw when we did the two-sample t-test. And that's what we're going to do in our next class.